friends. In this video, we will study the measurement of self-inductance using Anderson's bridge. The Anderson's bridge it is the most popular and very important bridge which is used for the measurement of self-inductance in terms of a standard capacitor. So let us start with our topic. So this Anderson's bridge, it is a modification of the Maxwell inductance capacitance bridge, which is also used for measurement of self-inductance. Here, the Anderson's bridge, it measures self-inductance by comparing its value or by getting its value in terms of a standard capacitor. Now, Anderson's bridge, it is a type of alternating current bridge. So this bridge, it consists of four arms having four impedances Z1, Z2, Z3 and Z4, and out of these four impedances, one impedance is unknown, that is the impedance which we want to measure, and the remaining three impedances are known to us. The impedances, they are the combination of the electrical parameters like resistance, inductance and the capacitor. So Anderson bridge, it will consist of four arms AB, BC, CD and DA. In these arms, we will have the four impedances Z1, Z2, Z3 and Z4. And out of these impedances, Z1 is the unknown impedance, and Z1, Z3, Z4, they are the known impedances. Impedances are a combination of the resistance, capacitor or the inductor. It can be a series combination also, or it can be a parallel combination also. Also in this bridge, we will have a detector which is used to obtain the balance condition for the alternating current bridge. Balance condition for a bridge network is the condition when the detector, it gives us the null deflection. Also for the power supply to the bridge network, we will have an alternating voltage source. Okay. Alternating voltage source will also be there, which will provide the power supply to the bridge network. So there are three main components. We are having the impedances, we are having a detector and an alternating voltage source in the bridge network. Now this bridge is said to be balanced, means when this detector is giving us the null deflection, and at this balancing we have the balance equation, which is Z1 Z4 is equals to Z2 Z3. This is the general balance equation for an alternating current bridge. It says that the product of the magnitude of the impedances which are present in the opposite pair of arms, they are equal to each other. So Z1, Z4, they are present in the opposite pair of arms. Z2, Z3, they are also present in the opposite pair of arms. So their product is equal. Okay. So here we know the value of Z2, Z3 and Z4 because they are the known impedances. So we can get the value of this unknown impedance Z1 in terms of these known values. Okay. So here, because this Anderson bridge is used for the measurement of self-inductance, so our unknown impedance will be the self-inductance, and we are going to measure the value of this self-inductance in terms of these known parameters. Okay. So let's see the circuit diagram of this Anderson bridge and then get this balance equation and then further calculate the value of the self-inductance. So this is the circuit diagram for the inductance bridge. You can see it is having 4 arms just like a normal bridge network. In this arms we are having the impedances, which are the combination of inductance, resistance and the capacitor. In arm AB we are having the unknown inductance, that is Lx, which is having an internal, or we can say an effective resistance Rx, connected in series with the resistance R1. Then here R3, it is a known non-inductive resistance R3. R2 is also a known resistance, and R4 is also a known resistance. In arm DE, we are having a known non-inductive resistance R, and here we are having a standard capacitor C. So if we see a normal bridge network, it will have only these 4 arms: AB, BC, CD and DA. Here we have additionally connected this capacitor and the resistance in between it. Okay, so this makes the circuit of the inductance bridge somewhat complicated, and also this is very important bridge. Okay. So let's see the configuration of all the arms and how we can represent the 4 impedances Z1, Z2, Z3 and Z4. First we are having the arm AB. Now in arm AB we were having the unknown inductance Lx. Rx and connected in series with R1. So this is the impedance in the arm AB. Now this impedance, let us suppose it is represented by Z1. So Z1 will be equal to Rx plus Lx plus R1. So Rx plus series combination of this, when we represent this inductance Lx, we write it as XL. So XL is what? J omega L. Okay. So here we will write it as J omega Lx plus this R1 is also in series with it, so R1 resistance. So this was the impedance in the arm AB, that is Z1. Next we are having the arm BC. So arm BC is what? It is the resistance R3 only. So R3 is a known non-inductive resistance. So if we represent it by the impedance Z3, so Z3 will be equals to R3 only. Then we have arm AD. The arm AD is also the resistance R2 only. So R2 is a known non-inductive resistance. Then we are having the arm CD. In arm CD, we are having the resistance R4. In CD, we are having this R4. So we can represent Z4 as R4. Non-inductive means that these resistances are not having any self-inductance in them associated with it. They are purely resistive. So non-inductive resistance R4. So Z4 will be equals to R4. Now here we are having 2 arms also, the arm CE and the arm DE. CE and DE. So arm CE is the standard capacitor C. A known non-inductive resistance R. So if we talk about the impedance between the arm DC, here first we have this CD arm. Now if this arm is considered this DC arm, so it will be the series combination of R and C. Okay, so if we consider only this DC part, this part, so it will be the series combination of this resistance R and the capacitor. So we are going to write it as the impedance Z DC, it will be equal to R plus the XC, that is the capacitive reactance XC, and XC is equals to 1 upon J omega C. So it will be equals to R upon 1 plus J omega C. Now we know that when the bridge is said to be balanced, then at the balance equation, means when the bridge is balanced, the detector, it will give us the null deflection. Null deflection means the point B and E, they are at the same potential. It means that no current is flowing in this arm, and the current I1, it is equal to the current I3. Okay, so one equation we can write at the balance. We know that at balance, no current is flowing through the detector. So this will act as an open circuit, and the current I1 will be equal to the current I3. Also we know that this current I2, it is splitting in two arms. So I2 will be equals to IR plus I4. So we can write here that I2 is equals to I4 plus IR. Okay, or we can say that this IR and IC, they are same, because whatever is IR, no current is flowing through this detector, so IR will be equals to IC. So we can say that I2, it is equal to I4 plus this IC. Because IR is equals to IC. Okay. Another equation is, we know that when the detector, it is giving us null deflection, it means that B and E are at the same potential. So this potential drop across the arm AB, it will be equal to the potential drop across the arm AD. Okay, or we can say that across the arm AE. Okay, so this potential drop E1, it will be equal to E2. So at balance, we have got another equation, E1 is equals to E2. So we have got these three equations. Now this capacitor C, it is connected between the points C and E. So whatever is the voltage drop across the capacitor, that will be the voltage drop across this R3, because when the bridge is balanced, we say that the B and E points, they are at the same potential. So this E3 voltage drop will be equal to the voltage drop across the capacitor also. So E3 is what? The voltage drop across this resistance, that is I3R3. And the voltage drop across this capacitor will be, current is IC. So voltage drop will be IC upon omega J omega C. Okay, so we have got another equation, E3 is equals to I3R3, or it is equal to IC upon J omega C. So this is our fourth equation. Okay. Now from first equation, we know that I1 is equals to I3. So we can replace this I3 by I1. So we can write I1 R3 is equal to IC upon J omega C. This is another equation. Now from this equation, if we get the value of IC will be equal to I1 J omega C R3. So from this fifth equation, we have got the value of the capacitor current, which is IC equals to I1 J omega C R3. Okay, this is termed as a sixth equation. Now, if we write the general balance equation for an alternating current, which says that Z1, Z4 is equals to Z2, Z3. Okay, so here we are having the Z1 as I1 plus, if we write the balance equation, means this even equation, what we have written, that E1 is equals to E2. This balance equation which we have written, equation number 3. So value of E1 will be I1 small r1 plus capital R1 plus J omega L1. And E2 is what? I2 R2 plus IC R. How? Let's see in the figure. E1 is the voltage drop across this inductor and the resistance. Across the inductor, we are having a resistance also. So, two resistances are there, Rx and R1, and one inductor is there. So, current multiplied with the total resistance. Total resistance is small r1 plus capital R1 plus J omega L1. We have represented this Rx, that is capital Rx, as a small r1 here. Okay. You can write it here, Rx is equals to small r1. Now, the E2 is the voltage drop across this AD arm, that is AE, the complete AE arm, because detector is giving us null deflection. So B and E potential points are at same potential. So voltage drop across AB and AE will be equal. So it will be I2R2 plus the voltage drop across this resistance. So current is IR and resistance is small r. Now this IR current, we have already got that this current is equals to IC. So it will be ICR. Okay. So here I have written E1 and E2 values. Now E1 is equals to E2. So we are going to equate them. Now this is our seventh equation. Now substituting the value of the IC current, which we have already obtained in equation number 6, we have obtained the value of the current IC. So we are going to put the value of IC in this seventh equation. Now just simplifying this equation, multiply I1 inside. Now these terms are also having I1 in it and this is also having I1. So we can shift this value to the left hand side. So taking I1 common from this part, we will get I1 small r1 plus capital R1 plus J omega L1 minus J omega C R3 and R is equals to I2 R2. Okay, this is our equation number 8. Now again in the Anderson's bridge, if we see the bridge network, we are having the arm CD and this arm if detector is giving us the null deflection, it means it's an open circuit. So the potential drop across this resistance plus this capacitance and the potential drop across this R4, they will be equal because this is not an arm. R and C, they will come in series with each other, and this series combination will be in parallel combination with this R4 resistance. So in parallel combination, the potential drop is same. So potential drop across these two and potential drop across this R4, they will be equal. Now the current in this arm is I2. You can see here we are having the I2. Okay, and this I2 is equals to IR plus I4. We have already written this. I2 is equals to IR plus I4. So if we want to calculate this IR, it will be equals to this IR is equals to IC current, because IR is the current which is flowing in IC. No current is flowing through this detector. So IR will be equal to this IC. Okay. Now if we write the potential drop across this resistance and the capacitor, it will be the current multiplied with the the equivalent impedance. Okay. So current is what? IC, and resistance is, or we can say equivalent resistance is R plus 1 upon j omega C, and this will be equal to the I4 R4. Okay. Now this IC we have already calculated its value, so its value is I1 j omega C R3, and here we are having R plus 1 upon j omega C. And here I4 can be written as the difference of I2 and IC, because IR and IC are same. So I2 can be written as IC plus I4, or we can say I4 is equals to I2 minus IC. So here I am writing it as I2 minus IC multiplied with R4. Again we can put the value of IC. So I2 minus IC is what? I1 j omega C R3 and multiplied with R4. So this is our another equation number 9. Now from the equation number 8 and equation number 9, if we equate the real and the imaginary parts, we can get the value of the resistance R1 and the inductance L1. Here if we equate the value of the imaginary parts and the real parts, and here also if we equate the imaginary and the real parts, then we can get the value of R1 and L1 as R1 will be equals to R2 R3 upon R4 minus of small r1, and L1 will be equals to C R3 by R4 . This is the value of L1. So in the bridge network, we have to find out the value of the self-inductance Lx, that is L1, okay, and the resistance R1, that is capital R1. So we have find out the value of this self-inductance in terms of the standard capacitor C. You can see that L1 and C, they are having a relationship between them. So with the help of inductance bridge, we can measure the self-inductance in terms of a standard capacitor. Now coming to the phasor diagram of this bridge. The phasor diagram shows the relationship between the phasors, or we can say the vectors of current and the voltages which are across the bridge network. So in this bridge network we are having the various voltages like E1, E2, E3 and E4, and currents like I1, I2, I3, I4, IC was there, the current across the capacitor. So we can have the relationship between these currents and voltages in the phasor diagram. Now before drawing the phasor diagram, we should have one concept clear in our mind, that what is the relationship between the current and voltages in a resistance, in a inductor and a capacitor. In a resistance, the voltage and the current, they are in same phase with each other. So if we talk about the resistance, that is resistance, voltage and current, they will be in same phase with each other. If we talk about an capacitor, so in capacitor the voltage, it lags behind the current by 90 degree. If we talk about an inductor, so in an inductor the voltage, it leads the current by 90 degree. So these relationships should be known to us, so it will be easy for us to draw the phasor diagram. Now in the phasor diagram we will have to take a reference phasor, so that all the other phasors and vectors, they can be drawn with respect to it. So here we will take the phasor for the current I1 as our reference phasor, and all the other currents and voltages, they will be drawn with respect to it. So I1 is the current flowing in the arm AB. So in the phasor diagram, we will draw the current I1 as our reference phasor. So this arm AB, it is having the resistances, two resistances are there and one inductor is there. Now current across this arm is I1. Okay, and if we see the voltage drop across this resistance will be I1 R1. So this I1 R1 and the current I1, they will be in same phase with each other. Also the current across this small R1, that will be in same phase with the current I1. So we are having two voltage drop due to the resistances. One is I1 R1 and another is I1 small R1. So we are getting the sum of it, and it will be in the same phase with the current. So here we will draw the phasor for this, which is I1 capital R1 plus small R1. Now the voltage drop across this inductor will be I1 omega L1. So this I1 omega L1, it will be 90 degree leading the current. So I1 is the current, so voltage drop will be I1 omega L1. Okay, now this I1 R1 plus this small R1 and this I1 omega L1, this is the total voltage drop across the arm AB. Okay, and this total voltage drop is what? Even. So if we draw the resultant phasor for these two vectors, then it will be the total EMF. So total EMF is E1. Okay, sum of this I1 omega L1 and I1 capital R1 plus small r1. Now this total EMF, that was equal to, when this bridge is in the balance condition, then this E1 will be equal to this E2, that is voltage drop across AE. Now in this AE we are having two resistances, that is this R2 also and this small r also. Okay, so this I1 R1 plus small R1, that will be equal to I2 capital R2 plus small r also. Okay, now coming to this right hand side. Now in this right hand side we have seen that this I1 current, it is equal to the current I3, okay, and the voltage drop E3 is equals to I3 R3. So in place of I3 we can write I1 also, okay. So I1 we have already drawn here, so on the same line we can draw I1 R3 also, or we can say this is what, E3. Now, when this bridge is balanced, then no current is flowing through this. So, this E3 will be equal to the voltage drop across this CE or across this capacitor. So, capacitor voltage drop will be IC upon the omega C. Okay. That is the voltage drop, current divided by the resistance, or current into the capacitive reactance, okay, and capacitive reactance is 1 upon omega C. So here we have this I1 R3 equals to E3, so E3, or we can say it is equal to IC upon omega C. Now this is the voltage drop across the capacitor. So current, if we talk about the capacitor here, capacitor voltage, it lags the current by 90 degree. So voltage is here, so current will be 90 degree ahead of it. So we will draw the current at 90 degree angle from it. This is the current IC, okay. Now same current, IC current, it is flowing through this resistance also. So if we talk about this resistance, voltage drop across this will be current multiplied with the resistance. Current is what? IC, and resistance is R. So this ICR will be in same phase with the current IC. So IC we have drawn here. ICR will be drawn on the same line, okay. Now this I2, it is the sum of IR plus I4. I4 is this current and IC is the current flowing in this sum. So I2 current, here we have drawn this I1 R1 plus small r1. Now this was IC upon omega C, okay. So if this is IC, we can draw IC over here also, okay, on this line. Here also IC can be written. Also we are having this ICR. This is here. So ICR can be drawn here also. Okay. Now this ICR and this IC upon omega C, it is equal to this E4, because when we are talking about the E4 voltage drop, it is the sum of the voltage drop across this resistance plus this capacitor. Also it is equal to the voltage drop across this resistance also. So this resistance was having the current I4 and voltage drop will be I4 R4. They will be in same phase, okay. So here we are having ICR and this was IC upon omega C, voltage drop across capacitor and voltage drop across the resistance. If we draw its resultant, so its resultant will be equal to E4, and E4 is what? I4 R4. And because this is the voltage drop across the resistance, so current should be drawn on the same line. This is I4, and here we have written that I2 is equals to IR plus I4, or we can say I2 is equals to IC plus I4. So here we are having I4, here we are having IC. If we draw it resultant, so its resultant will be this is the current I2, okay. So we have drawn all the voltages and the currents over this phasor diagram. Again, let's see, we are having the current I1 current and I1 R1 plus R1, that is the voltage drop across this resistance and the effective resistance of this coil, that will be in the same phase, so they are drawn on the same line. I1 omega L1 will be at 90° ahead of it. Voltage in case of inductor, it is leading the current by 90°, so this is drawn here. Their resultant will be equal to even. If we talk about E2, then E2 will be the sum of this I2R2 plus this IRR. So I2R2 and this I2, they will be in same phase. Okay, I2R2 and E2, they will be if I2 is drawn here, then E2 is also here. So E2 will be equals to I2 R2 on the same line. If we talk about E3, it is I3 R3. We have drawn E3 here, E4 is there. So even E2, E3, E4, if we extend their vectors, then we will get the resultant EMF E, because E is the sum of E1 plus E3, or we can say E is the sum of E2 plus E4. So this is our resultant total EMF E. Here also one relationship was between the currents I2. I2 is equals to IC plus I4. So we have drawn their resultant here. There was also one resultant between the voltages ICR plus IC upon omega C, that was equal to E4. So we have drawn the phasors of all the currents and voltages which are there in the bridge network. So the relationship between the phasors can be easily accessed through this phasor diagram. Now coming to the advantages and disadvantages of this Inductance bridge. The advantages of this bridge are that it can be used for the measurement of wide range of inductances. Second advantage is that in this Inductance bridge, we have used a capacitor which is a fixed standard capacitor, whereas in the Maxwell inductance capacitance bridge, we use the capacitor which is a variable capacitor. So here fixed capacitor is used instead of a variable capacitor. Third advantage is that it can be used for the accurate measurement of the capacitance also, which is in the terms of inductance. Earlier we have studied the measurement of self-inductance through this bridge. We can measure capacitance also, and the value of the capacitor will be in terms of the inductance. Next advantage is that the balance condition in this bridge can be easily obtained as compared to the Maxwell inductance capacitance bridge. So these were the advantages of the Inductance bridge. If we talk about the disadvantage, then disadvantage is that this bridge is very complicated because there are many components involved in this bridge. So the circuit of this Inductance bridge is very complicated. Also, we have seen that we require many components in this circuit. So this makes this bridge, because many components are involved, so this makes bridge complicated also and also expensive. Also, this Anderson's bridge, it cannot be shielded very easily, because here you can see in the bridge network we are having a junction point involved in it. This is the junction. This is the junction point involved E. So here the shielding of this bridge, Anderson's bridge, it is very difficult. So these are the advantages and disadvantages of the Anderson's bridge. So you can see that we can measure the value of the self-inductance in terms of a fixed standard capacitor by using this Anderson's bridge. So I hope that this topic is clear to you. Thank you.